Our second capstone this morning and our final capstone for this year's senior class is by Sebastian Cramer, and he'll be defending the following thesis. Quantum entanglement can be used to design technology that allows the instantaneous teleportation of information over immeasurable distances. Please welcome Sebastian.
Computer technology has developed drastically throughout history. As computers continue to develop, they're capable of providing services to humanity that would have never before otherwise been possible. One rapidly expanding frontier of science is that of space exploration. As this frontier continues to expand, it seems very likely that in the near future, some kind of a space exploration team will be exploring the deeper regions of space. The farther away these teams get from Earth, the longer it will take to communicate with them. As of today, computers communicate through radio waves, which travel at the speed of light. While light travels very fast, it does take a specific amount of time to travel. And if a space exploration team were to be a distance of 5 light years away from Earth, it would take 5 years for them to send a radio transmission to Earth, and 5 years for them to receive a response. It would be necessary to develop a more effective, more efficient method of communication for the safety and efficiency of these teams. Quantum entanglement can be used to design technology which allows the instantaneous teleportation of information over immeasurable distances. Now, just as no good basketball coach would try to start explaining to his team how to develop complicated plays and screens without first ensuring they are familiar with the fundamentals of dribbling and shooting, I would not try to explain how a quantum computer could be designed without first explaining what a quantum particle is and how it behaves. Charged particles, such as protons and electrons, create conditions in the field around them, in the space around them that we call fields. All of the conditions that these charged particles create make up the electromagnetic field. The charge of a particle does not mean anything intrinsic about it, but rather, to say that a particle has a positive or negative charge describes how that particle will affect other particles around it. It follows a well-known rule: likes repel and opposites attract. A negatively charged particle, like an electron, creates a condition in the electromagnetic field that repels negatively charged particles and attracts positively charged ones. As these particles move around in the electromagnetic field, their movement creates ripples much like the waves you see in the ocean. These electromagnetic waves can take on a variety of forms and be used for many different purposes. Some of the slowest oscillating electromagnetic waves are called radio waves, and they can be detected by radio devices and used to transmit information. If electromagnetic waves oscillate faster, they'll become the phenomenon we call light, which is visible to our eyes and helps us to form images in our brain. If electromagnetic waves oscillate even faster, they could become X-rays or gamma rays. All of these different forms of electromagnetic wave can be used for different purposes. It is possible for electromagnetic waves to oscillate so fast that they start to act like particles. We call these particle-like waves quantum particles, and they follow the laws of quantum physics. Electrons are the most important example of a quantum particle for our purposes. Quantum physics is entirely different from Newtonian physics, and it's absolutely impossible to understand. So let's jump in. Quantum physics allows quantum particles to take on some very strange and unusual behaviors that seem so strange to us, not because they've never happened before, but because we have no experience of them. The different laws of Newtonian physics include that of gravitation, electromagnetism, and nuclear reactions. And they all make sense to us because we see them happen every day. A ball falls to the ground, and you know that was gravity, and two magnets attract each other, and you know that was electromagnetism. These things seem very familiar, but to someone who had never experienced them before, they would be very unusual. This is the same reason that quantum physics seems so unusual to you and I, because we've never seen it before. Professor Brent Yates of Ohio State University began his course on quantum physics with this summary. Quantum physics, by nature, is inherently a statistical field. A particle can never be predicted with absolute certainty, only with certain probabilities of being in a particular state. Even stranger is the idea that a particle is not in any given state at once, but rather all states until it is observed. Once observed, a particle is then fixed in the observed state. Professor Gates touches on several important points of quantum physics with the summary. The first is that of the uncertainty principle. The uncertainty principle is a law that governs the behavior of quantum particles. If a quantum particle has a known starting location, the uncertainty principle states that we will be unable to know with certainty the exact starting momentum of the particle, and therefore, the particle could end up in any one of several different final locations. Likewise, it is possible that we would know the starting momentum of the particle, but then we would not be able to know the initial position. Therefore, it is still possible for the particle to end up in any one of several different final locations. The uncertainty principle governs this strange behavior of quantum particles and allows them to do things that normal particles that we see every day would never be able to do. The next important note that Professor Gates makes is that of superposition. Superposition is a quantum particle's ability to possess multiple contrary characteristics simultaneously. All this means is that a quantum particle can do two different things at the same time. You'll see here on the screen that we have a quantum particle that is spinning up and down at the same time. This seems impossible that a particle could possibly be multitasking and doing two exactly opposite things at the same time, but this is how quantum particles operate. In an experiment done by the California Institute of Technology and reviewed by the group PRX Quantum, concluded that the only way to explain the behavior of quantum particles is they are able to do something like this, spin up and down at the same time. Quantum particles experience a phenomenon called decoherence, which is the tendency of quantum particles to lose their superposition of states when interacting in a high energy environment. This phenomenon is not so unusual to us, as many particles in the world around us experience decoherence. If you watch this quantum particle, when it is measured or observed, it is interacting in a higher energy environment, and it now takes on a specific state, in this case, spinning up instead of up and down at the same time, and will continue to do so as long as it is being observed. A great analogy for this in the real world is that of a bowling ball in a bowling alley. If a bowling ball is sliding down a bowling alley, it will have a specific direction, a specific speed, and a specific degree of spin. And nothing will change that until it interacts with its environment outside of itself. If it is to hit a pin or a gutter, then it will change its direction, spin, and speed. But until then, it will keep doing the same thing it was doing before. Quantum particles are no different. They will be able to exist in a superposition of states, spinning up and down at the same time, until acted on by a high energy environment. All of these behaviors of quantum particles are very unusual, but this is the nature of quantum physics. Another such strange behavior of quantum particles is their capability of quantum entanglement. Quantum entanglement is the essential concept within quantum physics that allows for the possibility of quantum computers. In entanglement, the properties of one particle affect the properties of another, even if the particles are separated by a great distance. Quantum entanglement is a non-local interaction in which two particles affect each other, even when they're nowhere near each other. You'll see here on the screen that we have two particles, and when placed in a super cold environment in which almost all motion stops, these particles can pair up and become what we call a Cooper pair. They will now mirror each other's motion. Cooper pairs, when in a superposition of states, will have two particles both spinning up and down at the same time. And no matter how far apart these particles get, they will maintain the superposition of states, unless one of them is acted on by the outside environment. Once this happens, the acted on particle will take on a definite state. In this case, the acted on particle takes on the state of spinning up. The other particle immediately reflects this motion by spinning down. These particles are non-locally correlated. Non-local correlation is something that we experience in the world around us all the time. For example, if you're looking for your shoes, but you only find one of them, you can know information about a missing shoe even though you can't see it. If you find your left shoe, you could perfectly describe and imagine the right shoe even though you're nowhere near it. Quantum particles are the same way. If in two entangled quantum particles, if one of them is spinning up, the other one is now spinning down. This non-local correlation is not the unusual thing. It is the non-local interaction that is so strange to us. Non-local interaction in which the action of the first particle starting to spin up causes the other particle to start spinning down seems very strange. Now, if you're thinking that this is impossible, you're not alone. One of the smartest men in the world, Albert Einstein, did not think this was possible. In his 1935 paper, published with Boris Podolsky and Nathan Rosen, he questioned the possibility of quantum mechanics altogether. He called quantum entanglement spooky action at a distance, and believed that it was impossible for two particles to interact non-locally. However, given more recent experiments and research, it seems that Einstein was wrong, and quantum entanglement is possible, and particles can interact with one another while being located nowhere near each other. Paul Quiet, a physics researcher at the University of Illinois, concluded his 1994 experiment this way. Recently, we have pointed out that it is possible to make interaction-free quantum mechanical measurements in which the existence of an object in a given region of space may be ascertained seemingly without interacting with it. This possibility is non-classical, and that it relies on the wave-particle duality. This non-local interaction of quantum entanglement is critical to the development of quantum computers. Today, computers store information in a unit we call a bit, a binary digit that represents information as a 0 or a 1. Alone, a bit is almost useless, as it can only store two different types of information, 0 or 1. However, computers put bits into strings of 8 called bytes, and these bytes are capable of representing 256 different combinations of information. The more bytes a computer has, the more files a computer can store in the form of text, letters, images, numbers, colors, or videos. Computers can attain very large file sizes, but the problem is that the larger they get, the more time they take the computer to send and process them. Furthermore, computers are limited in their communication speed by the speed of radio waves traveling in the atmosphere. If two computers today need to send an email from one side of the earth to the other, it happens relatively quickly, as the radio waves are traveling at the speed of light. But back to our initial example, if a computer today were to try to send a transmission to another computer 5 light years away, it would take 5 years for that transmission to take place. Quantum computers can fix this problem. Quantum computers store information in a unit called a qubit, a quantum bit, that is an electron that represents information by spinning up or spinning down. But since quantum particles are capable of superposition, quantum bits can also store information by spinning up and down at the same time. This third possibility allows quantum computers to store 1 to 2 times as much information as a traditional computer in the same amount of space. This is one advantage of quantum computers, but the more notable one is that of their increased communication speed. Quantum computers can teleport information because they can send signals to each other without ever having the message cross the space in between them. The motion of the qubits of one quantum computer is immediately reflected in the motion of the qubits of the other, and therefore information can be transferred without crossing the space in between instantaneously. Quantum computers capable of teleporting information communicate much faster than traditional computers, and therefore could be more useful in this scientific field. Leah Hessler, a writer for the Argonne National Laboratory, says, "Quantum internet, a network over which qubits, in which information is stored in qubits and shared over long distances through entanglement, would transform the fields of data storage, precision sensing and computing, ushering in a new era of communication." It is not so difficult to get a general understanding of quantum physics. It just takes the realization that the complexity of it is due to the fact that you and I have never experienced it before. Quantum particles capable of entanglement can communicate information through mirroring each other's motions. Quantum computers can communicate much faster than any traditional computer ever can, and they can serve many purposes in the world to come. Thank you.